Welcome to our second lecture of GIS concepts. And so this is talking about our data types, coordinate systems, and scales. So between the two courses that you're taking with me right now, this is looking at the aspects of the world in just another tool, right? So remote sensing is one because we capture information from a sensor and we get that data, but we can't really put thematic information there. So like we can't say, oh, there's this much population, or we can't say, from looking at an aerial photo, we can't say this is the direction of a migration of caribou. We're not able to do that. But with GIS, we're able to take the remote sensing data that we have and make it even more powerful by adding that information to it. So with this one, what GIS really is it represents the world as a map. And so we're taking a map, which in this case or data, we're taking data and creating something that makes sense, that shows us relationships, and it shows us the world in a version of symbols that we can use on our computer or on a piece of paper. So for example, here's a map. We have some labels that are being listed here. That's what allows us to understand what's going on in those locations. We've got little boxes here, which are probably buildings. We can see roads. We can maybe a railway line. Maybe that's what that is. See water. We can identify it even without me looking at a legend to this. I can still identify information. So now we can looking at all that. Now we can really start breaking it down into categories of what are these symbols trying to show us. So the first one we have is the point features, which you can see here. And then we have line features, which is our roads. And then we have polygon features, which is like these waste ponds, for example. So these three major categories are what maps use as symbols in order to portray what is going on in our world. We also use annotations, which is our labels, that allow us to provide more information to the reader so that they have a better understanding and a little bit more of a grasp on what we're trying to show in that map. So because we're dealing with symbols, we have to be concerned about generalization and we have to be concerned about scale. Now this is the scale. We talk about that in remote sensing as well, so if you haven't taken that course, then that's okay. So the scale is the ratio of the size, actually this should be reversed, the size on the map to the size on the ground. So we're always going to have a 1 to something. So what that means is if I measure 1 centimeter on my map, then I might have 500 centimeters on the ground. So that would be a scale of 1 to 500. So it's always unitless. Not always, but that would be a lie. There's different ways to represent it. One of them is a unitless ratio of that way, so I can use any kind of measurement tool that I want or measurement unit, and I can apply it. So here's a 1 to 5,000 map approximately. So if you were to take this to your screen and you were to measure between 2 points and then you applied the scale, you could actually calculate the distance on the ground. This one is about 1 to 30 million. So again, I can measure across the entire country, but I can't see a lot of detail, right? So the closer the more I zoom in to a location, the more detail I can see. Now this is where we get into really very specific terms that are called small, medium, large, right? So those three terms are where we can start referring to scale. So what is a small scale? What is a large scale? This gets really confusing because there's actually really no line that says, okay, now you have a small scale, now you have a large scale. They're all about relative to each other. But if I have a small scale, for example, a small scale means that I have very small details on there, so I can't see them. There's not much information on there because everything is really, really small. So a small scale means I've completely zoomed out. So this 1 to 30 million is a small scale. A large scale means I've zoomed in and now I can see a lot of larger details, and there's more details there. And so the more you zoom in, the larger the scale. So that gets really confusing. So just kind of watch that term. Think of it, how big are my small details, right? If I can see small things and it's large, then I know that I have a large scale. If I can't see any small details and there's nothing there, then it is a small scale. Okay. So the scale is important for a map because it influences the way you generalize your features. So how do I represent my information? What information am I going to show? What's important to show? So for example, in this one, we should see the water, we see the boundaries of all the states, and we see Portsmouth. That's it. We don't see much else. This one, we see little buildings, we see all kinds of stuff. We even have contours in there. We got all kinds of stuff going on in this one. So again, because it is a large scale, we can show more information, and we don't need to generalize quite as much. But this one, we have to really be picky about what we're actually showing. So just as a quick review, the map scale is the ratio of the distance on the map to the distance on the ground. So for example, if we measured this to be 2.5 centimeters, and we know that our scale is 1 to 100,000, then we can take 100,000, multiply by 2.5, divide by 1, and we get 250,000 centimeters, or 2.5 kilometers on the ground. And that would give us our distance from one side of this to the other. The ratio itself is dimensionless, like I mentioned before. So you can use centimeters, millimeters, inches, whatever you like. And the actual formula that you will see is scale equals map distance divided by ground distance. But you will see me refer to it as 1 over S equals dm over dg. And the reason I do that is because when you're calculating scale, if you do map divided by ground distance, you're going to end up with this weird 0 point something number. And you will always end up 0 point something number. So that doesn't make any sense. Like, what does that mean? That's not a scale. That's a number. That's like a value below 1. So to avoid that, I like to have the 1 over S, because then you're calculating S. You're not actually calculating 1 divided by S. So the other key thing is that your map distance and your ground distance must be in the same unit. So they have to be the same. All right, so continuing on from there, a larger denominator gives a smaller fraction, which gives a smaller scale map, okay? It shows a larger area, but the features look smaller with less detail. So this is a small scale map, right? Small scale. A smaller denominator gives a larger fraction. So mathematically, right? You think 1 divided by a really big number gives you a really small number. 1 divided by a biggish number gives you a bigger number. And so that is a larger scale map. So this would be a larger scale map. It shows a smaller area, but the features are larger. So for example, 1 to 5,000 there. So you can really see a lot more detail in that one. Again, there's no line. It's not like, oh, at this number, suddenly you have a large or small scale. That doesn't exist. It's really more relative to each other. So then getting into data models. So we have 2 major data models that we use in GIS. The first one's vector models. The other one is raster models. So for those of you taking my remote sensing class with me, that everything is in rasters because we have pixels. Rasters are all pixels and pixelation, where vectors is lines, points, areas. That's all they are. So, but they do have some other really important features that I want to also bring up here. So we got lines, points, areas, right? Everything is built, so points themselves are just a point, but the lines are built on vertices or nodes. Nodes are what start and end a line. So you can see the nodes there are the special ones. The vertices are where all the bends in the line are. And the vertices also go around the entire polygon. Okay, so you can click, 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 click all the way around an entire pond, and you're going to have 100 vertices in that polygon. So what's important though with this vector model, not only do you have points, lines, and polygons that are also developed by vertices and nodes, it is a series of x and y coordinates, and that's all those vertices that are stored, and they have some sort of rectangular coordinate system. So when I say that, you can think Cartesian coordinate system if you prefer that terminology. It means you have an x value and a y value. So we can put it on a graph and put 0, 0 here, and they're going to have some sort of location in that graph. So we've already talked about this. The features can have one of 3 geometry types, points, lines, or polygons, and each of those have the data in them that's saved, right? So the polygon, in this case, is going to have a whole bunch of x, y, z, or not z. No, we're not getting into 3 dimensions here. X and y coordinates all the way around. So we have all of that here. And that's going to be stored as part of that polygon. Okay? And all of those, and it knows as a polygon, all of those points are related to one single shape. For the line, we're going to end up having, there will be 4 vertices and 2 nodes, so the start and end, and then the 4 vertices, and the line is going to save that as it's an x, y, z for each individual point along here, and then it says, okay, now those are connected. With points, you just get one x, y, z coordinate, and that is it. That's how it's saved. So then we can kind of expand on that, and what this is the key feature with vector data is that you can actually include information that is not spatial information with the same x, y, z information, whether it's a point, line, or area, or polygon, sorry. So here, for example, we can have population. There's 2 different population distances or differences. We can have number of households. We can have the name. We can abbreviate it. We can have all kinds of different categories of data that we can extract from this. And this is all saved as part of that vector data. So for example, if you're looking at households that like tax information or who owns what property information, it's really important to have vector information or vector saved, because now you have exact numbers of like where the corners of their property are as a polygon. But you can also include the name of the owner. You can include how many people are there. You can include how many houses are on that particular lot. All of that information is saved as an attribute with that shape. So this table that you have, you can bring into the GIS software that you're using, and you can showcase that different information. So for example, here they've got different colors of the states based on whatever they're showing, and then they've also got points showing other information, right? So all of this is a different attribute. Each color can be changed for each attribute, and so forth. We can look at very specific data as well, so we can say, hey, where is Washington? And we can identify that by just clicking on the line in the table, and it's going to provide me with all that information along that line in that table. So really, really powerful. The next thing that's important with, especially specifically to ArcGIS, is the feature classes. So a feature class is a collection of similar objects with the same attributes stored in a single unit. So what does that mean? That means that, for example, if I want a feature class of houses, I can only save houses in that feature class, because houses are going to have a type of address. It's going to have maybe the city that it's in. It's going to have number of people that live in it. It's going to have maybe square footage of the house. It could have a whole bunch of stuff like that. So the feature class, the attributes are all going to be the same for every feature that you have. So if I use my house, I have individual houses, and I can save each individual house with all the information I need in it. I can't, though, have a house and then a store and then a gas station, because now the gas station isn't going to have many people living there, right? And so it doesn't really fit in that class. So we wouldn't want to do that. So again, so here we're seeing a whole bunch of objects. We have areas, state name, states. That's a feature class. Here's a river one. So what's a river feature class? You can see here this is a polygon. So we have polygons of the states. This one we have polylines, or a line, which is a shape. Then we got names, the system that it comes off of, etc. And then we have the capitals of the different states, right? So we can, again, they have different attributes that are all the same. Polygon, line, and point. So each of these are their own feature class, and they're saved as a separate table. And they can only contain, another key thing is they can only contain one type of geometry. So you can't create a point class, feature class, and expect to save polygons in there. It has to be a polygon class feature class in order for you to save it as a polygon. So some of the advantages, I've kind of listed a few of them as we go. You have precise locations of features because it can be infinitely small as to where that location is. We can store many attributes. Those tables have no limit to them. It's flexible when you're trying to do different symbology, that you're trying to change maybe the way it looks, the way you label it. That's what cartography is. Cartography is that art and science of creating an actual map. It's also very compact for storage. So, I mean, even though you can save a lot of information, it's still a text file, really, in the end, a CSV file. So it doesn't take up a lot of memory. And it is really great for certain types of analysis, for lengths, areas, connections, because of the mathematical properties of having XY data, right? So that, and especially for points, because we remember we have all those nodes and all those vertices, we can really do any kind of analysis with that kind of information. So if you're looking, for example, as to how has the grizzly bear habitat been reduced over the years, now we're looking at an area, we can also look at lengths of like how much it ventures out from its usual habitat, and how has that changed over the years. So that would be an ideal way, or an ideal application of using vector data. So the other data model is the raster data model. And this is what you would be working with in remote sensing, but we can do rasters of other information. So we can look at any kind of pixel which is continuous, and we can just put them all together and make a picture out of it. And there's no like missing information in between. Well, sometimes there is, but that's to be determined later. So there is an XY location, but that XY location accuracy is limited by the size of the pixel. So if my pixels are 1 meter by 1 meter, that is as accurate as I'm going to get, because I don't know where in that 1 meter by 1 meter that something falls in there. We can identify columns and rows. So columns are the ones that go vertical, rows go horizontal. The 0 is actually at the top, to make things confusing. If you're just looking at the raster itself, unless you have it with a coordinate system. If it has a coordinate system, then the coordinate system takes over. But if I'm looking at pixel 1, 2, it's going to be row 1, pixel 2, so that would be that point there. So n rows by m columns, it can be any size. And then once we georeference it, then that takes over. Okay, so that's our georeferencing. Oh, and what's missing on here, a key feature about this is that each pixel can only hold one piece of information, and can only show one piece of information. There in remote sensing, we talk about composites, which we'll get to, and each pixel can hold 3 values depending on to create an image, but really it ends up being the same. It's the same value. All it's saying is that these 3 pieces of information are going to show this thing. So one layer of a raster can only hold one, because remember, a composite is actually 3 layers put together. So raster is only one of those layers, and so it can only hold one piece of information. And that's what we're going to get. So if this one is elevation, that's all it's going to show is elevation. If it's showing precipitation, it's only showing the amount of precipitation per pixel. That is all it can show. I cannot add, this pixel's owner to it. Right? There's no table that comes with it. It is merely just value of pixel for each value of pixel. That's all you're going to see. All right, so the next subject in this is coordinate systems. So this is an important concept for looking at this, because if we're going to put anything in the real world, it needs to follow a coordinate system. So our systems we use for the most part are 2 or 3 dimensional. There are 4-dimensional space as well, but we won't be getting into that in this class. So the easiest way to start with this is with 2 dimensions and then moving into 3 dimensions later, and that's what we're going to be doing in this course. There's also 2 different types of coordinate systems. So one is an unprojected coordinate system, the other one is a projected coordinate system. Unprojected coordinate systems are based on the actual sphere of the Earth itself. So you can think of it as a globe. It's like a globe system. There is geographic coordinate systems. So the geographic coordinate system is based on a sphere of the Earth. So it says okay, the shape of the Earth is an actual sphere, and that is our latitude and longitude. So the way that it's identified, the way that it's kind of tweaked and manipulated, because you're taking this spherical information and putting it onto a screen, right? It's a flat screen on top of that. So there's some distortion that comes with that when you're trying to show it on the computer screen. So that's why there's different kinds of coordinate systems that come with it. But if you use a unprojected coordinate system, which WGS84 is one of them, that just says, okay, on the Earth, if I was on the real Earth, the location is here in this particular location on the globe. A projected coordinate system is a fun one in reverse of that. So now we're taking the globe and we're trying to project it onto a flat piece of paper. So the projected coordinate system, as you can see, we've got this round Earth, and then we've got a light bulb inside the Earth, and it projects out onto the piece of paper here. So it converts it into flat planar coordinates, which means I can now use meters. It is really hard to do any kind of distance calculation, any kind of scale calculation, any angular calculation with latitude and longitude. You really need to switch it into a planar coordinate system to do that math. So that's why we do that, and it makes it so much easier. So you're going to see things such as like UTM, 3TM, 10TM, depending on the industry you work in. And it's going to project onto a piece of paper like that. So you get a nice flat one, which is what our screens are. Right? So we project our Earth onto a screen, and it gives us these nice coordinates. There is a lot of mathematics that go into it, and that is not the place for this course to cover that, but you're taking, all you're doing is taking this Earth and going here. I do suggest that if you have an opportunity, watch my potato and tennis ball video. That one will really help, and I'll make sure that that is uploaded for everyone to check out. So we take 3D coordinates in this case, and we go to 2D coordinates, and that's what happens here. You can still add those 3D back in as like contours or hillshade or any of the other ones, but for the most part, it's just an XY coordinate system. So let's dive in a little bit more into the geographic coordinate system. So we're going to locate a point by referencing its distance from a fixed point and the angle this line makes with a fixed line. It's like, whoa, what does that mean? So we have this circle on the equator, and then we have the poles as well. We have a very particular radius of the circle. So we go to the center of the circle, and we find the point that we're looking for. And so what we're trying to do is determine from the equator and from some 0 point, what does that angle? So we can get our latitude, which is the angle from the equator going up, and longitude, which is the angle from that 0 point going around in an counterclockwise direction. Both of them are counterclockwise here. So there is a video as well that I will show in class, and we can watch that, and it does a really good job of explaining the latitude and longitude in a little bit more detail as well. So here is, so that I'll show the video, but here's some more detail on it. So latitude itself is measured from the equator, and you have to say whether it's north or south, because otherwise nobody knows. So north is positive, south is negative, or you can call it N or S. N for north, S for south. So Calgary is located at approximately 51 degrees north latitude, and so you can find it located there. Longitude is measured in counterclockwise from the prime meridian, which runs through Greenwich, and in England. There was a big fight about which one was the rose line, right? And I talk about that, and that's the beginning of the argument. And then England won. They run out, explained why they needed it, and then so now the 0 goes through Greenwich. So if you ever travel there, you can always check out the 0 line. So there is west and east. West is actually negative, and east is positive. So remember, it's going counterclockwise. So Calgary is located at 114 degrees west. And so if we were to look at it mathematically, this is what it would look like. So we have the radius from the center of the Earth to our point. And then we have two angles. So we have our longitude and we have our latitude angles there. So that's what it looks like in terms of the Cartesian coordinates. So if we were at 80 degrees east, 55 degrees north, that's what it's going to be, 80 degrees from the 0 line and from the 55 degrees north of the equator. And you can locate it there. So prime meridian and equator. So the rectangular coordinate system, this is something you guys have worked with in school for quite a few years, I'm sure. And if you've forgotten, that's okay. So this is as if there is an infinite piece of paper in front of us, and there's actually really no natural reference point or origin. So you can set something, say like, hey, there's a natural stop here, and therefore we're going to put our 0 there. But the way that we work with it in GIS is that a lot of our projected coordinate systems don't really have an official 0. It can change depending on where you're located. So the origin it's arbitrary. 0, 0 is where you want it, or where the system that has been developed for you is at. So that also, so that also is kind of a key thing where the unprojected coordinate systems, they have a 0 right at the center of the Earth, so that it makes it easy to follow. But these are just X and Y, or you can hear the words northings and eastings as well, where northings is going north, eastings is going east. Anything going the opposite direction becomes negative. And so you end up with a point at some location. And generally speaking, we're going to be using these rectangular coordinate systems because, again, easier to do math, easier to calculate areas, everything else. And you're not working with degrees, you're working with meters, which makes things, again, much easier. So that is a quick summary of our different coordinate systems. And if you are in my class, then we will be using this data to work with the GPS data that we're going to go out and collect. So you're going to collect the data according to the lab, and we'll discuss that in class. So I look forward to seeing you in class.